Hello everyone and welcome back to the UniDec tutorial series. My name is Marius and today I will give a brief explanation of how the UniDec algorithm works and cover the parameters in the Quick Controls tab. The Quick Controls tab makes UniDec's deconvolution faster to adjust and more user-friendly. However, each of these parameters has a lot of depth, and better understanding of each will improve your deconvolutions. I will be using example data in UniDec so that you can follow along. I will use the ADH example data, which contains the dimer, trimer, and tetramer of alcohol dehydrogenase, although the dimer and trimer are in much lower abundance compared to the tetramer. Before we go deeper into the quick controls, I want to give a brief explanation on the UniDec algorithm. UniDec goes through multiple iterations of 3 steps to create a 2-dimensional charge versus M over Z matrix from the original 1-dimensional mass spectrum, which contains the most likely charge states assignments for each M over Z data point. The 2-dimensional charge versus M over Z matrix is shown in the plot directly below the original M over Z spectrum post-deconvolution. Initially, UniDec assumes that all charge states are possible for a M over Z peak. To quickly show this, I will deconvolve the ADH data and deliberately halt the deconvolution algorithm before it has the chance to converge by changing the number of iterations used for the deconvolution to 0. I'll explain what convergence means later. See how all charge states are assigned for each M over Z value? Some M over Z values don't make it all the way to the top charge states. And the reason for this is because those charge states, those higher charge states, would give a mass value that would exceed our 180 kilodalton mass limit. Furthermore, the vertical smears for each of these M over Z values indicate that the intensities for each M over Z are spread over multiple charge states. So we need to filter this 2-dimensional matrix to find the charge states that are most likely, which is the first step in the UniDec algorithm. Now, UniDec has 3 ways to assign unique charge states for each M over Z value: the charge state distribution, the mass distribution, or the isotope distribution. Note, these are not mutually exclusive and they can be used as complementary combinations. UniDec will assign charge states based on the charge state distribution if the smooth charge states distributions checkbox is on. This tells UniDec to expect a smooth charge state distribution and that each charge state should have neighboring charge states that are Z plus 1 and Z minus 1 from the initial Z charge. We will go into more specifics later in the video. With that assumption, UniDec applies a filter to the 2-dimensional matrix of charge versus M over Z to increase the intensities of charge states with support from neighboring charge states and decrease the intensities of charge states that lack neighboring peaks. In this case, we can see that the plus 26 charge state has support from the neighboring charge states. However, for example, the 32 plus charge state does not have support from the neighboring 31 and 33 charge states because there's little to no intensity at those M over Z values for those potential charge states. To the right, we can see that the charge state distribution is narrowed from the 2-dimensional charge versus M over Z matrix with 0 iterations. After applying the filter, we now need to go back and compare the matrix with the data again. In the second step, UniDec will create a simulated spectrum. It will first sum the 2-dimensional matrix along the charge axis to create a simulated 1-dimensional mass spectrum that has the same dimensions as the original data. This simulated mass spectrum can be convolved with a known peak shape and width so that each peak has a minimum defined peak shape and width. I'll explain this in more detail later. At the end of the second step, we have a simulated mass spectrum that hopefully matches the data. In the third step, the simulated mass spectrum is compared to the actual mass spectrum. If a data point in the simulated mass spectrum has a lower intensity than the same m/z value with the actual mass spectrum, the UniDec will increase the intensity of all charge states at that projected m/z. If a data point in the simulated spectrum has a higher intensity than the actual m/z peak, then UniDec will lower the intensity of the charge states for that m/z. UniDec goes through multiple iterations of these 3 steps, filtering the charge state distribution, summing the 2-dimensional charge versus m/z matrix into a 1-dimensional mass spectrum, which can be convolved with an entered peak width and shape, then finally compares the intensities to the actual m/z spectrum. The algorithm converges when, through multiple iterations of the algorithm, the intensities in the projected mass spectrum match the intensities in the actual mass spectrum, or they stop changing between iterations. Now I will go in further depth in each parameter that affects the deconvolution. As I stated previously, turning on the smooth charge state distributions option will tell UniDec to expect that a particular peak with a charge state of z will have adjacent peaks with charge states at z+1 and z-1. Checking this box alters the charge smooth width in the Advanced Deconvolution Parameters tab, setting it to the default value of 1. The width that you enter tells UniDec how many charge states to consider on each side, but a value of 1 is usually optimal. That is why the Quick Controls presents a simple checkbox for whether you expect a smooth charge state distribution or not. With the charge smoothing applied, you'll see with just 10 iterations that UniDec has predicted the charge states for each m/z value. In more detail, charge smoothing uses a mean filter, also called a rolling average or boxcar filter, in log space throughout the charge state distribution for a given mass. The charge smooth width specifies how many data points to include in the smoothing. In this case, where a width of 1 is used, for each potential mass value, the log intensity for charge state z, z-1, and z+1 will be averaged and set as the intensity at data point z for that mass. Thus, as you can see, there is no charge state, for example, at 32, because there is no intensity at 31 or 33 for this m/z. The log intensities are used to prevent broadening of the charge state distribution that can otherwise occur if the mean filter was used on the normal intensity values. One hidden feature: if a negative value is set for the charge smooth function, it will change how the charge state distribution is smoothed. Rather than using a logarithmic mean filter, a negative value will tell UniDec to smooth the charge state distribution with a simple Gaussian filter that has a width set by the value in the box. Note, unlike the positive values, which are rounded to the nearest integer, the negative values can be non-integers, like 0.5. This is very similar to the Gaussian smoothing that we used in Part 2 data processing. This Gaussian smoothing will broaden the charge state distribution more than the logarithmic mean function. Most applications should use the default of +1, but some with wider charge state distributions would benefit from experimenting with negative values and with different widths. As I stated previously, after the first step of the algorithm, the filtered 2-dimensional charge versus m/z matrix is summed along the charge axis. This creates a 1-dimensional simulated mass spectrum with the same dimensions as the data. We can then convolve the simulated spectrum with the known peak shape, which is defined by the peak width and peak shape function parameters. This convolution is ignored if the full width half max is 0. The convolution will effectively create a copy of the peak shape at each m/z point in the summed simulated spectrum that has a non-zero intensity, and then sum these together. In other words, it tells UniDec that when simulated the spectrum, assume all peaks have a defined minimum peak width and shape. Larger peak widths and more complex shape functions are not a problem for the algorithm because it can add together multiple adjacent data points to create a more complex pattern. Clicking the automatic m/z peak width option will tell UniDec to determine the peak shape and full width half max from the processed mass spectrum, and it will tell it to use this value in the second step of the deconvolution. UniDec does this by finding the most abundant peak, isolating it, and fitting it to either a Gaussian, Lorentzian, or split Gaussian-Lorentzian peak, and then finding the best fit from these three. These peak width parameters can be manually set in the additional deconvolution parameters tab. Furthermore, under Tools Peak Width tool, you can select and fit different peaks manually. Here, I'll select the main peak and click Fit Peak. Clicking OK will update the tab with a new peak fit. The split Gaussian-Lorentzian in this case captures the longer tail on the high mass side of the peak, which is due to adduction. You can return to the automatic peak shape and peak width by selecting Tools, Automatic Peak Width, or Control W. It's better to use the lowest full width half max possible to capture all of the features in the data, but lower full width half max values can lead to more noise in the deconvolved mass spectrum. To better show this, I will set the full width half max to 5. You can see in the raw m/z mass spectrum that the fit data contains some of the noise in the raw data, which will carry over into the deconvolved mass spectrum. Now, these other artifact peaks in the deconvolved mass spectrum are due to misassigned charge states or multiple charge states that are assigned for a single m/z value. Here you can see that these artifact peaks are caused by misassignments of the main 26 and 27 charge state mass peaks. We'll go into how to remove these satellite peaks later. However, a higher full width half max can lead to underfitting the data, resulting in a less well resolved deconvolved mass spectrum that is cleaner but does not capture the fine details present in the spectrum. Overall, the full width half max can be a very useful parameter to tune the deconvolution. At the moment, you have to enter one full width half max for the whole spectrum, but future versions plan to implement variable peak widths across the spectrum. Smoothing neighboring points is useful for cleaning up more complex data. For example, in the ADH data, we see reoccurring artifact peaks in the deconvolved mass spectrum. This is caused by multiple data points around a charge state for a potential mass value. Clicking the sum or lots option will help smooth nearby points and will help clean up the deconvolved mass spectrum. The smooth nearby points option affects the point smooth width in the additional deconvolution parameters tab. Briefly, smoothing nearby points tells UniDec that neighboring data points should have the same charge state, which is usually true in continuously sampled data. In more detail, this function will smooth neighboring data points within each charge state with a mean filter. To better show how each charge state contributes to the deconvolved mass spectrum, I will go to Analysis, Plot by Charge. In the Data with Offset Isolated Species plot, you can see how each charge state contributes to the overall mass spectrum. This function smooths the neighboring data points in each of these charge states by running a mean filter across each of these lines. The width of data points to smooth with the mean filter is set by the value in the box. There are 4 options for smooth nearby points. in the quick controls: none, some, lots, and other. Clicking the sum option will turn the point smooth function on and set it to the default, which is 1. The lots option will set the point smooth to 10. Using a wider point smooth width may broaden the peak slightly. Using a point smooth other than 1 or 10 will switch the smooth nearby points option to other. However, in cases where point smooth is not enough to diminish most of the artifacts, it's better to use a combination of point smooth with the next option, which is suppress artifacts. The Suppress Artifacts feature sets the beta parameter in the Additional Deconvolution Parameters tab. The beta parameter is useful for deconvolving mass spectra that contain broad mass peaks and for reducing artifacts in the data, such as harmonic or satellite peaks where the charge states are partially misassigned. The beta parameter uses a softmax function to push each data point towards having a single charge state. It will push the most abundant charge state in the two-dimensional charge versus M over Z matrix for each M over Z to be more intense. Note that this is discrete data. The oval shape of the data in the plot here is just a part of the plotting. To show the discrete data, I will go to the additional plotting parameters and click discrete data and click replot. The amount of increased intensity is determined by the beta parameter, and larger values will more aggressively push towards a single charge state assignment for each M over Z value. The softmax function is used in the first step of the UniDec algorithm that we mentioned previously and works as an additional filter to the charge and mass smoothing. The 4 options for suppress artifacts are none, some, lots, and other. Clicking the sum option will set the beta value at 50, which is a medium setting that will suppress some artifacts. Clicking lots will set the beta value at 500, which helps to remove the remaining artifacts from the ADH spectrum. However, using the lots option may distort the deconvolution, especially when there are overlapping peaks in the spectrum. In some highly overlapping spectra, manually adjusting the beta value to lower values like 5 would be useful. To learn more about the beta function, refer to the first softmax function paper shown here. The mass difference function can be used to assign charge states in the first step of the UniDec algorithm, similar to charge smoothing. However, rather than assigning based on the charge state distribution, mass difference assigns charge states based on the mass distribution. To better explain this section, I will be using the POPC nanodiscs example data. Nanodiscs are nanoscale lipid bilayer platforms that are useful for studying membrane interactions. They have relatively low polydispersity and each are composed of a variable number of phospholipids, such that there could be a nanodisc with 149, 150, and 151 phospholipids that are held together by 2 membrane scaffold protein belts, or MSPs. The imported mass spectrum shows multiple intact POPC nanodiscs in a typical charge state distribution. The key point is that each intact nanodisc is separated by a repeating phospholipid mass, the POPC lipid, similar to a repeating monomer unit in a polymer. In these cases, the mass difference filter can be used to help UniDec assign charge states by using the input mass spacing as a prior assumption. Because we know the mass spacing, we can assign charge states from the M over Z differences. Similar to the charge smoothing, mass difference suggests that each M over Z should have a neighboring peak that is M plus NM over Z and M minus NM over Z, where big M is the value in Daltons entered in the box. In this case, M would be the mass of the repeating lipid, POPC, which is 760 Daltons. Using an M that does not reflect the true mass spacing can distort the deconvolution. However, there are tools like the FFT window and autocorrelation which can help determine repeating mass differences. Furthermore, in the Additional Deconvolution Parameters tab, mass smooth width can be used to set how many neighboring mass peaks to consider. In other words, it sets how large n should be for the n plus n m over z and the m minus nm over z. Similar to charge smoothing, mass smooth width will use a log mean filter that will smooth the mass distribution. By default, the mass smooth width is set to 0, but clicking the box sets it to 1. However, it may be more useful to experiment with higher n values when broad mass distributions are expected, which may help smooth the mass distribution and reduce artifacts. Similar to charge state smoothing, setting the value to a negative number activates a hidden feature to switch the filter type from a log mean filter to a Gaussian filter, which can be very beneficial for wider mass distributions. With that covered, you should feel prepared to deconvolve a wide variety of mass spectra. If the defaults don't work, try different combinations of parameters to improve your deconvolution. The next video will cover the remaining parameters in the additional deconvolution parameters tab. Thank you for choosing UniDec.